Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to cover some key concepts that will help us better understand how chemical reactions behave in water. In the first objective, we're going to begin by reviewing some essential concepts, focusing on aqueous acid-base reactions. Then we'll discuss how to determine the chemistry of a solution and describe whether a reaction should be treated as a stoichiometry problem or as an equilibrium problem. Next, we'll explore equilibria in solutions and cover the common ion effect, which plays a critical role in many applications. Finally, we'll discuss titrations and buffers. We'll use the Henderson-Hasselbalch equation to explain how buffers work to maintain a stable pH, and we're going to learn how to apply these principles to acid-base titrations. With that introduction, let's go ahead and get started with Objective 1. To solve problems involving acid-base reactions, buffers, and titrations, it's essential to correctly identify the chemical equation that describes what is happening. Whether the reaction involves weak acids and bases or strong acids and bases, knowing the type of interaction helps us determine how the reaction behaves. This also tells us whether we should solve the problem using stoichiometric calculations or whether we should solve the problem using equilibrium analysis. In most cases, we use net ionic equations to represent acid-base reactions. Net ionic equations focus only on the parts of the reaction that are actually changing, and it leaves out spectator ions that do not participate. So let's walk through the key species we're going to encounter in these reactions, starting with HA. HA represents a neutral weak acid. A- represents the negatively charged conjugate base of HA. B represents a neutral weak base, and HB plus represents the positively charged conjugate base of B. Now, for strong acids and strong bases, things are a little different. Strong acids are shown in net ionic equations as the hydronium ion, which is written as H3O+, and strong bases appear as the hydroxide ion, written as OH-. Now let's go over the 5 most common types of acid-base reactions. This is going to be important for our later discussion. The first type is the reaction of a weak acid with water. In this reaction, the weak acid releases a proton to water, forming its conjugate base and the hydronium ion like you see written in this first reaction. Alternatively, if the weak acid exists as a positively charged ion, it reacts with water to form a neutral weak base and the hydronium ion. The second type is the reaction of a weak base with water. In this case, the weak base reacts with water by accepting a proton and forming its conjugate acid and the hydroxide ion. Alternatively, a negatively charged weak base can react with water to reform its corresponding weak acid and produce hydroxide ions. The third type is the reaction between a strong acid and a strong base. Since both the strong acid and the strong base fully dissociate, they react completely to produce water. This type of reaction goes to completion, meaning that equilibrium is not involved. The fourth type is the reaction of a weak acid with a strong base. In this reaction, the strong base accepts a proton from the weak acid, forming the conjugate base of the weak acid and water. Alternatively, a positively charged weak acid can donate its proton to the hydroxide ion, forming a weak base and water. The fifth type is the reaction between a strong acid and a weak base. The hydronium ion from the strong acid donates a proton to the weak base, forming the conjugate acid of the weak base and water. Alternatively, if the weak base is negatively charged, the hydronium ion donates a proton to form the corresponding weak acid and water. Understanding these different types of reactions is really important because it's going to help us decide whether the reaction is best described as a stoichiometry or an equilibrium problem. For reactions that reach equilibrium, such as those involving weak acids or weak bases, an ice table will help determine the concentrations of each species at equilibrium. In these cases, it's important to account for how the concentrations change over time as the system reaches a balance between the forward and reverse reactions. To rephrase, if the reaction is described as an equilibrium process, it will be represented with a double arrow. This indicates that there's a balance between the forward and reverse reactions. For these problems, an ice table is used to calculate the concentrations at equilibrium. We're familiar with ice tables, we've seen them before, and again, it's important to reiterate that ice tables rely on concentrations, not moles, throughout the calculation. What about if the reaction goes to completion? If the reaction goes to completion, such as in the case of strong acids and strong bases, a BCA table is the correct tool. Now, this is a new tool that we have not yet been introduced to, but we're going to describe in detail in Objective 3. We're still going to define it here as well. This method focuses on the amounts of reactants and products in terms of moles or millimoles, tracking how much of each substance is consumed or produced until the reaction finishes. To reiterate, if the reaction goes to completion, it's going to be represented with a one-way arrow, showing that the reactants are fully converted into products with no reverse reaction. In these cases, a BCA table is used to track the changes in moles or millimoles rather than concentrations, and BCA stands for before, change, and after. A key point in stoichiometric problems is identifying the limiting reactant, which is completely consumed during the reaction. This reactant determines how much product can be formed and when the reaction stops. With that, we can go ahead and move into Objective 2. Objective 2 is titled Solution Equilibrii, and we're going to start with reviewing net ionic equations. One useful way to represent reactions occurring in aqueous solutions is through net ionic equations. These equations focus on the ions that participate directly in the reaction, and they help us simplify and understand the chemistry that is actually taking place. We've seen examples of these equations before, and now we're just going to review the process of writing net ionic equations one more time. The 3 steps for writing net ionic equation is as follows. The first step is to write the molecular equation. The molecular equation shows all of the reactants and products in their neutral, undissociated form. Then in the next step, we want to write the total or complete ionic equation. In this step, all strong electrolytes are dissociated into ions because this is how they actually exist in solution. And this table helps us determine what is a soluble ionic compound and what is an insoluble ionic compound. Finally, to get the net ionic equation, we remove the spectator ions. These are ions that appear on both sides of the equation without undergoing any change. The net ionic equation contains only the species that participate directly in the chemical reaction. Now, net ionic equations are incredibly useful for 3 reasons. First, they focus on the actual chemical change by eliminating spectator ions, and that helps us see which species are actually reacting. 2, they reveal the driving force behind the reaction, whether it's the formation of a precipitate, a gas, or water. And finally, they highlight the similarities among different reactions, particularly those involving electrolytes, which helps us recognize patterns across different systems. Now that we've reviewed net ionic equations, let's dive into solubility equilibria. Specifically, we want to look at how sparingly soluble salts behave in water and how we can quantify their solubility using the solubility product constant known as KSP. When an ionic compound dissolves in water, it breaks apart into its constituent ions. For salts that are only sparingly soluble, meaning they do not dissolve easily, the dissolution process reaches equilibrium between the dissolved ions and the undissolved solid. This process can be represented by the following reaction you see here. At equilibrium, the concentration of the ions are related through the solubility product constant, or KSP. The key point is that solids are not included in the equilibrium expression because their concentration is considered constant. So for this reaction of our ionic compound AMBN, if we were to write the KSP, it would just be the concentration of the ions raised to their respective stoichiometric coefficients, and AMBN, that ionic compound, is not included because it is a solid. From here, we can begin to discuss saturation and the role of KSP. As an ionic solid dissolves in water, the system moves toward saturation. Saturation occurs when the concentration of dissolved ions reaches the maximum allowed by the KSP value at that temperature. At this point, no more solute can dissolve, and any additional solid will precipitate out of the solution. To determine whether a solution is unsaturated, saturated, or supersaturated, we use the ion product. The ion product is calculated in the same way as KSP. And we take that value for our ion product and we compare it to the solubility product constant, KSP, and that allows us to predict whether precipitation will occur. If the ion product is less than the solubility product constant, then the solution is unsaturated, meaning more solute can still dissolve. If the ion product is equal to the solubility product constant, then the solution is saturated and at equilibrium. And that means no more solute will dissolve, but no precipitation will occur either. If the ion product is greater than the solubility product constant, then the solution is supersaturated, meaning it contains more dissolved solute than the equilibrium amount, and precipitation will occur to restore balance. Now, as a side note here, in some textbooks, you're going to see the ion product, IP, written as QSP, where Q indicates that it is a reaction quotient. Regardless of the name, the principle remains the same. Comparing the current concentration of ions to the solubility product constant is going to help us predict whether the solution is stable or if precipitation will form. In short, our key takeaway points are the following. KSP quantifies the solubility of sparingly soluble salts, and it provides insight into the equilibrium between dissolved ions and solid precipitate. And second, by calculating the ion product and comparing it to KSP, we can predict whether a solution will remain stable or if precipitation will occur. With that, let's jump into a practice problem. This problem asks, will a precipitate form if 25 milliliters of 0.04 molar barium nitrate is mixed with 45 milliliters of 0.1 molar sodium fluoride? And we're given the KSP for barium fluoride, and it's equal to 1.7 times 10 to the negative 6. We're being asked to determine if barium fluoride will precipitate from the solution. And the relevant ions here are going to be barium, 2 plus, and fluoride, minus 1. We can determine if precipitation will occur by comparing the ion product we're going to calculate to the KSP value we're given. In order to calculate the ion product, we have to determine the concentration of the relevant ions after mixing the two solutions. Mixing two solutions is, practically speaking, the same as diluting them, so we can actually use the solution by dilution equation. M1 V1 is equal to M2 V2. And we want to solve for M2 for both ions, barium and fluoride. Now V2, really quickly, this is going to be the new volume. It represents the total volume of the mixture, which in this case is just 25 milliliters plus 45 milliliters, and that's equal to 70 milliliters. Now again, we're solving for M2, so let's rearrange this equation to solve for M2. That's going to be equal to M1 V1 over V2. And we're going to use this equation to solve for the concentration of both ions of interest. And we're going to start with barium. The concentration for barium is going to be equal to M1 V1 over V2. M1 is going to be equal to 0.04 molar. That's given to us in the problem. And V1 is going to be equal to 25 milliliters, also given to us in the problem. We also just calculated V2, and we said V2 is equal to 70 milliliters. If we plug this into a calculator, we're going to get that the concentration of barium ions is equal to 0.0143 molar. Now we want to do the same thing for our fluoride ions. This is going to be equal to M1 V1 over V2. M1 is 0.1 molar. V1 is equal to 45 milliliters, and V2 is 70 milliliters. If we plug this into our calculator, we're going to get 0.0643 molar. Now that we have this information, we can start to think how we're going to calculate the ion product. The ion product is going to be the concentration of our ions raised to their respective stoichiometric coefficients. Notice that when we're forming barium fluoride, for one barium cation, we have two fluoride anions. So our ion product is going to be the concentration of our barium cations multiplied by the concentration of our fluoride anions raised to the power 2. Again, because for every barium cation we have two fluoride anions. Now we can go ahead and plug in the values we calculated. The concentration for barium cations is 0.0143, and the concentration for fluoride anions is 0.0643, and this value is going to be squared. If we plug this into a calculator, we're going to get that the ion product is equal to 5.9 times 10 to the negative 5. And we want to compare this value to the KSP, which is 1.7 times 10 to the negative 6. We quickly realize that the ion product is greater than the KSP, so the solution is supersaturated and precipitation will occur. Wonderful. Now we can move into our next topic. Our next topic is the common ion effect. This principle explains how the solubility of a compound decreases when one of the ions it produces is already present in the solution. The common ion effect is a direct consequence of Le Chatelier's principle, which states that a system at equilibrium will shift to minimize any changes imposed on it. In this case, when extra ions are added, the equilibrium adjusts to restore balance, often leading to a decrease in solubility. To see the common ion effect in action, let's look at the dissolution of magnesium phosphate, which is a sparingly soluble salt. When magnesium phosphate dissolves in water, it breaks apart into magnesium ions and phosphate ions. At equilibrium, the rate of dissolution of the solid equals the rate at which the ions recombine to form the solid again. In addition, the solubility of magnesium phosphate depends on the concentrations of magnesium ions and phosphate ions in solution. With that being said, let's now explore what happens when we introduce a common ion into the system. Imagine we add magnesium chloride to this solution. Magnesium chloride is a strong electrolyte, so it dissociates completely and it releases additional magnesium ions into the solution. As the concentration of magnesium ions increase, the system responds by shifting the equilibrium to the left towards the formation of more solid magnesium phosphate. This shift occurs because the system wants to reduce the excess magnesium ions and restore equilibrium. So as a result, more magnesium phosphate precipitates out of solution and the overall solubility of magnesium phosphate decreases. This process demonstrates the common ion effect, which states that the presence of an ion that is already part of the equilibrium suppresses the dissolution of the compound, leading to decreased solubility. Now, the common ion effect, it plays an important role in several areas of chemistry. It's important in precipitation reactions. The common ion effect helps predict whether a precipitate will form when two solutions are mixed. It's also important in buffer solutions. In buffers, the common ion effect helps maintain a stable pH, and we're going to get into that a little bit more in Objective 3. Let's go ahead, though, and tackle a practice problem. This problem says the KSP for lead 2 chloride is 1.6 times 10 to the negative 5 at 25 degrees Celsius. Determine the molar solubility of lead 2 chloride under the following conditions: A in pure water and B in 0.1 molar sodium chloride. Now, before we tackle part A and B, let's go ahead and write the reaction. Here we have solid lead 2 chloride in solution. It dissolves to give us lead 2 plus cations and chloride anions. And here we have a coefficient of 2 in front of chloride to make sure the reaction is balanced. From here, we can go ahead and write the KSP expression, keeping in mind that solids and liquids are not included. So our KSP is equal to the concentration of lead 2 plus multiplied by the concentration of chloride ions squared. Now we can start with part A. In pure water, there are no common ions present initially. So we can obtain the molar solubility by using an ICE table, where I stands for initial, C for change, E for equilibrium. Now, when we're starting off, we just have lead 2 chloride. It hasn't dissolved yet, so our initial concentration for our ions is 0. Over time, lead 2 chloride dissolves to give us some concentration of lead 2 plus and chloride ions. And here it's really important to note the ratio between these two ions. It's 1 to 2. So when we denote this change using the variable x, we want to use that ratio to express this change. So the change for lead 2 plus is plus x, and the change in concentration for chloride ions is plus 2x. And now we can write our equilibrium concentrations. For lead 2 plus, it's x, and for chloride, it's 2x. And we're going to use these equilibrium concentrations to rewrite our KSP expression. KSP is equal to x multiplied by 2x squared, and this is equal to 1.6 times 10 to the negative 5. Let's expand this part. This is x multiplied by 4x squared. That gives us 4x cubed, and that's equal to 1.6 times 10 to the negative 5. Now we can divide both sides by 4 and take the cube root, and we can get the value of x this way. X is equal to 0.016 molar. So that is for part A. What about for part B, when we have 0.1 molar sodium chloride? For part B, we're also going to set up an ice table similar to the one we saw in part A, but we have to pay close attention to two things here. First, the initial concentration of chloride ions is actually 0.1 molar. Now, this 0.1 molar concentration of chloride ions comes from sodium chloride, not from lead-2 chloride. Sodium chloride is a strong electrolyte that completely dissociates in solution, hence why we have an initial concentration of 0.1 for our chloride ions. Again, this is not coming from lead-2 chloride. Our initial concentration for lead-2 plus is still 0. Obviously, over time, lead-2 chloride is going to dissociate in solution, and we're going to form some concentration of lead-2 plus and chloride ions. And we're going to denote that change the same way we did for part A. Now our equilibrium concentrations for lead-2 plus is X, and for chloride it's 0.1 plus 2X. We can go ahead and rewrite our KSP based off of our equilibrium concentrations. That's going to be X multiplied by 0.1 plus 2X, and this is going to be squared, and that's equal to 1.6 times 10 to the negative 5. Now you can take this expression, you can plug it into a calculator like Desmos calculator, and it can solve for X. But if you're trying to do this quickly and have the math be a little easier, we can simplify this expression. Chloride is a common ion, and we said it comes from two sources, sodium chloride and lead-2 chloride. Since it's a common ion, it represses the ionization of the lead-2 chloride salt. In other words, it makes lead-2 chloride less soluble, and it makes the magnitude of X smaller than it was in pure water. So that considered, we can say that plus 2X is negligible, and we can get rid of that. And now we can solve the KSP as X multiplied by 0.1 squared, and that's equal to 1.6 times 10 to the negative 5. And this is really easy to solve for X. If we divide both sides by 0.1 squared, then X is going to be equal to 0.0016 molar. And there you have it. We've solved this problem. Now we can move into the last topic for this objective, and that is the effect of pH on solubility. The solubility of many salts is influenced by the pH of the solution, especially for salts that contain ions derived from weak bases. When the pH changes, it affects the equilibrium between the solid salt and the ions dissolved in the solution. Let's use calcium carbonate as an example to understand how this process works. When calcium carbonate dissolves in water, it separates into calcium ions and carbonate ions. At equilibrium, the concentrations of calcium and carbonate ions remain stable. However, the carbonate ion is the conjugate base of a weak acid, carbonic acid. This means that the solubility of calcium carbonate will be affected by changes in the pH of the solution. When the pH of the solution decreases, the concentration of hydrogen ions increases. And these hydrogen ions can react with the carbonate ions to form bicarbonate ions or carbonic acid. This reaction removes carbonate ions from the solution, reducing their concentration. And according to Le Chatelier's principle, the equilibrium for the dissolution of calcium carbonate is going to shift to the right to replace the carbonate ions that were removed by the hydrogen ions. As a result, more calcium carbonate dissolves, increasing the solubility of the salt in acidic conditions. Now let's take that idea and apply it to this example problem. This problem says which of the sparingly soluble salts below become more soluble as the pH is lowered. We have magnesium hydroxide, silver chloride, and calcium fluoride. Now, in order to determine if the pH of a solution will affect the solubility of a sparingly soluble salt, we have to focus on the anion. If the anion comes from a strong acid, it's going to serve as a spectator ion in acid-base reactions. That includes any one of the following anions you see here. Therefore, the solubility of any salt containing one of these anions is not affected by the pH. But if the anion is the conjugate base of a weak acid, then it is a weak base and it's going to react with hydronium ions. Examples include the following anions you see here. Salts containing these anions become more soluble as the pH is lowered. What we realize is that magnesium hydroxide and calcium fluoride contain those anions, and therefore they become more soluble as the pH is lowered. And with that, we've completed Objective 2. In the following video, we're going to cover Objective 3, which revolves around buffers and titration. Let me know if you have any questions about the content so far. Other than that, good luck, happy studying, and have a beautiful, beautiful day.